Okay, so yesterday we did an example from section H.2 where we found the area of a region, and we learned about the area formula for finding the area under the polar curve, uh, where the limits are a starting angle and an ending angle. Um, and here we want to find the area of a region that lies inside one polar curve and outside another, well, or one region, I should say, and outside another region. So let you copy this down, and then we'll go over it. Okay, so we want to find the area of the region that lies inside the circle, r equals 3 sine theta, and outside the cardioid, r equals 1 plus sine of theta. So what's the first thing you need to do in order to solve this problem? What's the first thing you have to do to solve this problem? I mean, how do we start the problem? That's right, Josiah. We have to graph it. We have to graph it. Okay, we have to graph it. So what I'd like you to do is on your calculator, go ahead and graph, and I will also move to my calculator here. Let me see, let me just get my calculator up here, one moment. Okay, one moment here. Okay. Just out of curiosity, class, do they make, like what I have is, of course, a TI calculator uh, program that projects the calculator on the screen. Do they make any of those for free offhand? Does anybody know offhand if they make like you know, I don't know. I can't imagine it would be free, but like a TI-8384 calculator that's on the computer that like is free. I've heard sometimes they have them for cell phones and stuff. So anybody heard of that type thing? Or I mean, of course I can investigate it. I've just never needed to worry about it before, you know. All right, let me see here. One moment here. So I want to share my application. Hold on here. All right, I have it up. There it is. Okay, so as you know here, we go to mode and we put our calculator in polar mode, and then that allows us to graph our polar curves. So the first one is 3 times the sine of theta, and the next one is 1 plus the sine of theta. Okay, so I have my two polar graphs, and let me know if you have any questions. I'm going to just kind of keep moving forward here if there are no questions. Okay, and I got to decide on a window. I know that the 3 sine theta, at largest it could be 3, and smallest it could be -3. So let's see, got to be a little bit careful here. But you know, the circle, you might not need to go from 0 to 2 pi to get the circle. So tell you what, let me just you know, put 0 to 2 pi. You know, I got to put something down. So 0 to 2 pi. And then for my theta step, I'll take the difference between my theta max and my theta min and divide it by like 10,000 points, just so it doesn't graph it so fast. And then for x min, I'll say -3. For x max 3, y scale 1, y min -3, y max 3. Okay, so far so good. All right, let's look at the graph. Okay, so it's graphing the circle first. Looks pretty good. Looks pretty good here. It's graphing the circle. And now it's graphing the cardioid. Should graph the cardioid. Let's see here. There we go. How many think this is absolutely cool? Any thumbs up? Okay, thank you, John. Thank you, Tyreek. Thank you, Robin. Thank you, Francesca. All right. Takes the calculator time to compute all these values. right? Maybe it's using an algorithm like, you know, Taylor-Maclaurin series or a polynomial, you know, to get these degrees, these angle values. To get the R values for angles. But at any rate, okay, so there, we got it. Now, what we have to do is we want the area, we want the area in the circle. The circle is the blue figure, and we want the area that lies inside the blue circle and outside the red cardioid. Okay, so that's going to be the area above the red cardioid and below the blue circle. All right, so so I'm going to get to the solution here, but are we okay with this? Are there any questions so far? So certainly for your exam, your final exam, these kind of problems where you are finding areas, I will want to see pictures. Pictures are part of the work. Okay, so it goes without saying. Right. Okay, so what is critical to find here between these two polar curves? What is definitely critical to find in order to do this problem? I mean, to find the area, we need a starting angle and an ending angle. What would those angles be? Like, how would we find the starting angle and the ending angle between for the area we're looking for? What do we have to do you think? What do you always have to do when you have two figures in a problem? What tends to be something that you have to do? What do you have to find? What points do you need to find? That's right, Robin. The points of intersection. Absolutely. So let me stop the graph there and now go back to the example itself. Okay, let's get to the solution here. Okay, so what I've done is I've drawn the, let me see here, one moment. I've drawn the, try to do this best I can, the blue circle, R equals R equals 3 times the sine of theta. And I've drawn the red cardioid. One moment. Okay. And the area that we want is this area here. Because that area is inside the circle, and outside the cardioid. So of course, what's going to be critical here is to find where does this black area begin? It begins right where it begins on the right side where the cardioid intersects the circle, and then on the left side it ends where the cardioid intersects the circle. Okay. Make that a little more. So that means we have to find the points of intersection. Well, to find the points of intersection, all you need to do is set the one polar curve equal to the other and solve for theta. And you're going to get theta equals pi over 6, which is 30 degrees. Well, when you set the two polar curves equal to each other, you're solving the sine of theta equals a half. Sine of theta is positive in the first and second quadrants, right? The first and second quadrants. So the first angle is 30 degrees, pi over 6. The second angle would be 150 degrees. Right? That's the other angle, 5 pi over 6. Okay. And if you notice on the picture here, the green angle lines, those are actually the green line on the right is the line with polar equation theta equals pi over 6. The green line on the left here is the polar equation, is the line with polar equation theta equals 5 pi over 6. And you can see just by looking at the angles that looks about right. Okay, this angle here is about 30 degrees, and this angle here is about 150 degrees. I mean, the picture's not perfect, but you get the general idea. So are there any questions so far? Any questions so far? Okay. And these notes here might be a little old. This is, let me see, in the textbook for the appendix. Let me just make sure. Here, one moment. Yeah, this is actually figure 5. If you look in your book, at least the book I have, the fourth edition, it should correspond to the ebook. This is actually figure 5 in the book. But now what we have to do is we have to find the area in black here. We have to find that black area. Well, what we can do, you see, is we can find, let me see here, I want to just say this the right way. We could find the area of the circle from theta equals pi over 6 to 5 pi over 6, and then subtract the area of the cardioid. Okay, so what I'm saying is we can find, let me see here, maybe, let's see, maybe I can do it in yellow. We can find this yellow area here. Okay, we can find that yellow area, which would be, the area is the integral 1/2 r squared d theta. So that would be 1/2 3 times the sine theta quantity squared d theta, where the angle goes from pi/6 to 5 pi/6. Find that area, and then subtract out the area of the cardioid going from pi/6 to 5 pi/6. Subtract out the area of the cardioid. And by doing that, you'll get the black area. So this is what you want to do. The area that you're looking for, the area A, is equal to the integral from pi/6 to 5 pi/6 times 1/2 3 sine theta squared d theta minus 1/2 times the integral from pi/6 to 5 pi/6 of 1/2 1 plus sine theta quantity squared. The first integral represents that yellow area, which is the area of the circle, the area underneath this, well, the area of the circle where your starting angle is pi/6 and your ending angle is 5 pi/6. And the second integral represents the area of the cardioid, where your starting angle is pi/6 and your ending angle is 5 pi/6. Just make it a little bit nice here, one moment. These are lines here, right? And this is your, kind of looks like a diamond there. All right, I mean, are there any questions so far? Oh, rise 1/2 written twice. The reason is, it isn't written twice. Good question, Josiah, but I know what you mean. You're taking one area here, the big area, and you're subtracting out a smaller area. To get the area of the black region, to get the area of this black region here, you have to take the difference of two areas. So what I've done is under each area here, under the first area, I've drawn a little picture of what that area represents. It's a little bit like, remember when we had to find the volume of a solid, where the solid was found by rotating a figure around an x-axis or y-axis or some axis, and we drew a picture of the two volumes, and then we subtract them, and that's the volume we want. It's the same principle here. The first integral represents the area of the circle, where you're restricting the circle to be the starting angle to be pi/6 and 5 pi/6. And then from that, you're subtracting the area under the cardioid, where you're restricting your angle to be from pi/6 to 5 pi/6. Josiah, does that make sense? Does that help you feel a little more comfortable? Oh, the integral in red has 2 1/2s. That's an error. Thank you. Good catching that. Ah, I see what I mean. I see what you mean. All right, yeah, there should not be a half here. Thank you, Josiah. Good catch. Thank you, Robin. Good catch. All right, all right. So now we have to integrate this. But again, anytime we can use symmetry uh, for to help us with computing our integrals, that's a good thing. I could figure out, okay, 3 times the sine of theta squared is 9, like for the first integral. That's 3 times the sine of theta quantity squared. That's 9 squared, 9 times the sine squared of theta. And hey, I could then substitute a trig identity for the sine squared of theta, which would be 1 minus cosine 2 theta over 2, and then integrate that from pi over 6 to 5 pi over 6 and get an answer. That's fine. I can do that, and I can do something similar for this right integral. However, I'm noticing that, halfway between 30 degrees, halfway between 30 degrees and 150 degrees is 90 degrees, right? 90 degrees is halfway between those two angles. And 90 degrees is a nice angle to evaluate sines and cosines at, okay? So would the function 3 times the sine of theta be, if we square it, would that function be symmetric about theta equals pi over 2? And the answer is yes. The answer is yes. Again, why don't we just go back to, let me see here. Well, what I've done here, is I've drawn a little picture of the sine of theta. Okay, but let me see here. Let's tell you what. The picture's not super clear. I mean, it's okay, but let me go back to the calculator here. Let's go back to that calculator. Application. Okay, let's go back there. And now I want to put the calculator in just regular mode, regular function mode. Okay. And I want to type in, I'll make it just sort of easy here. I'll type in 3 times the sine of 3 times the sine. No, I'm not doing this right. 3 times the sine of x squared. Okay. All right, 3 times the sine of x squared. And what I want to do is I'm going to look at that function where x min is pi over 6 and x max is 5 pi over 6. Okay. And for the scale, I'll use 5 pi over 6 minus pi over 6. And I'll divide that by 4. Maybe I want 4 tick marks in my graph. I know it's going to be a positive function, so I'll let y min be 0. I know that 9 is the highest value, or I should be careful here. 3 would be the highest value it could ever take. So y min will be 0, y max will be 3. And I want to graph this 3 times the sine of theta quantity, the quantity 3 times the sine of theta squared function, and see if it's symmetric about pi over 2. So I'll graph it. Now hold on here. I don't have, so what did I do wrong here? Oh, wait, let me check my mode. In radians, let me check my window here. Let me just change this to like 9 and graph here. Okay, so why did it, I mean, the sine of theta, oh, we're squaring it. Okay, so 3 times the sine of theta quantity squared. If the sine of theta is 1, which it is at 90 degrees, 3 squared is 9. So, okay, so for the window, I had to have my y max be 9. So what I've done here is I've actually drawn this 3 times the sine of theta quantity squared function, which is 9 times the sine squared of theta. I've drawn it from pi over 6 to 5 pi over 6, 30 degrees. That's 30 degrees to 150 degrees. 90 degrees is right in the middle, and you can see that this function is symmetric about 90 degrees. So that means that the function is symmetric about theta equals pi over 2, and the area to the area underneath 3 times the area underneath 9 times the sine squared of theta. The area underneath 9 times the sine squared of theta to the right of pi over 2 is the same as the area to the left of pi over 2, So what I'm saying is the area underneath this function, the area from pi over 6 to pi over 2, is the same as the area from pi over 2 to 5 pi over 6. And so that means that I can rewrite my integral. All right, I can rewrite my integral. And so if I go back to the solution here, okay, I can rewrite the integral. The first integral can be written, well, the first integral can be written as 2 times the integral, where the limits go from pi over 6 to pi over 2. So you notice I'm replacing the 5 pi over 6, I'm replacing that with pi over 2, but I'm doubling the area. If I double the area underneath this function from pi over 6 to pi over 2, that'll be the same as the area from pi over 6 to 5 pi over 6. And the same will follow, by the way, for the second function. If you graph 1 plus the sine of theta quantity squared, if you graph that on your calculator, you'll see that it is also symmetric about pi over 2. And so 2 times the area under that function, 1 plus sine of theta quantity squared, 2 times that the area from pi over 6 to pi over 2 is the same as the area from pi over 6 to 5 pi over 6. And so this is how, get that bracket in there a little better, this is how we get the second expression. And again, you don't need, and you can see the 2's right out front there, right? You know, distribute the 2 and you have it. Distribute the 2 on both integrals and you know, you're there. So I don't have to do this, I don't have to rewrite these integrals with these new limits from pi over 6 to pi over 2 and then multiply by 2. I don't have to do that, but it's going to make your life a little bit easier. Are there any questions on that? Are there any questions? And I'm sort of graphically showing you why these functions are symmetric about 90 degrees. You could prove that algebraically, but how many kind of like looking at the graphs to get just an intuitive feel? Okay, thank you, Josiah. Thank you, Tyreek. Excellent, excellent. I mean, you know, thank you, Francesca. Thank you. Yeah, and John, thank you. I mean, it's just kind of, it helps you feel comfortable seeing it, right? And we know that sines and cosines are symmetric about certain angles, and you know. Okay, so what I do then is, let me see now. Hold on, I got to look at my work here. Okay, so I combine, I distribute the two. 2 times a half is 1. 2 times the other half is 1. So I don't have to worry about the halves anymore. And then the difference of two integrals is the integral of the difference. So I'm going to take 9 sine squared of theta and subtract the 1 plus 2 sine theta plus sine squared theta. That's going to get me then 8 sine squared theta minus 1 minus 2 sine theta. Because 9 squared minus sine squared is 8 sine squared. And that gets us here. Okay, so these steps are important, you know. These steps, showing your work in these problems is important. And you know, there we are. There we are. Are there any questions going up to this step here? Okay, all right. Well, the sine squared of theta, of course, we're going to replace that. We're going to replace the sine squared of theta here with the identity 1/2 times 1 minus the cosine of 2 theta. And so we're going to get then the integral from pi over 6 to pi over 2 of 4 times 1 minus cosine 2 theta minus 1 minus 2 sine theta d theta. Are there any questions so far? It is critical, by the way, if you're going to do this kind of trick where you say, okay, the function's symmetric about like pi over 2, like we did here, and that helped us convert our limits. You do have to check that, okay? You do have to check that kind of thing. You can't just, make sure you at least graphically see it before you assume that a function's symmetric about an angle. Draw a picture of the graph, okay? And I realize, of course, that on the final exam, that's going to take time. These problems take time to do. These polar coordinate problems take time, okay? So I do recognize that. Again, which is another reason why I think breaking the exam up into 3 parts is better than just 2 parts. All right, let me get to the next page. So this is just algebra from here and integration. So you're going to get then, when you distribute the 4, you're going to get 4 minus 4 cosine of 2 theta minus 1 minus 2 sine theta. And then you combine like terms. Okay. And you'll get the integral from pi over 6 of 3 minus 4 cosine 2 theta minus 2 times the sine of theta. And then I left work out. Okay, so I'm just in the interest of saving a little time. So here, of course, work is needed. But I know you can do that work. I know you can get antiderivatives of all those functions and work it out. And when you do the work, you will get pi. Okay? And that is what WebAssign is going to want, and that's what I'm going to want. I do not want a decimal, and WebAssign is very picky on decimals, so make sure you give me a simplified radical form answer for all of these problems. Okay, are there any questions on that problem? I think I would like to do another one with you. Okay, and these appendix pages probably aren't accurate anymore. So, are there any questions before we move to the next example? And everybody has this copied okay? Okay, and incidentally, there's a problem on your WebAssign homework where it wants you to find the area of the inner loop of a curve. So for that problem, you're going to have to draw the curve and get your limit angles on the inner loop. And there's a help video on that. I think you'll need to look at the help video to do that one, but it's good. So I'm going to let you look at the help video for that one. Let's move on to another example. All right, we want to let me let you copy it down. Okay, so in this problem, we want to find the area of the region that lies inside the three-leaf rose, which is r equals 2 times the sine of 3 theta, and outside the circle, r equals 1. Okay, so what you need to do is you need to graph the both of these polar curves on your calculator and find an appropriate window. Okay, so Let's see here, one moment. All right, let me go actually to the calculator. Okay, mode, we'll put it back in polar. And then the y, let's see, we have what, 2 times the sine. So please make sure you're following along on your own calculator. Dang it. Okay, there's the first one. And then the second one is just circle r equals 1. Okay. We'll go to window. And let's see. I think I'm going to just use the same theta min, theta max I had before. Maybe the theta step, maybe I'll make it 2 pi, which is theta max, minus 0 over, instead of 10,000 points, maybe I'll do 5,000. Okay, it'll make the graph go a little quicker. Okay, and then hit graph. Okay, and obviously that's not a good window, right? So I got to go back to window here. Second quit. Ha! I got to wait for this to stop graphing, I guess. Hold on. So there we go. Not a very good window, right? All right, so here's the problem, the y min and the y max and the x min and the x max. So why don't I go from like -2 to 2, and never mind the phone, -2, 2, and -2 to 2. Just 1 minute. Hello. Okay, let's get the phone out of the way here. You gotta leave a message now, right? This is your time. All right, so the reason I'm using 2 is 2 times the sine of 3 theta. That radius would never be more than 2. So it's just, I'm just hoping that'll be a good window. All right, let's try to do a graph. Hey, there we go. Who's liking this? Yeah, I hear you. Let me see. Thank you, John. Thank you, Tyreek. Thank you, Robin. Thank you, Josiah. Thank you, Francesca. It's almost as good as the new James Bond movie that's going to come out, right? All right. There we go. That's right. Darius knows what I'm talking about. Thank you. So, all right, there's the picture. There's the picture, okay? And so now what you would do on your final exam, and you should be doing it on your homework too, you draw the picture, right? And then based on that, you can answer the question. Well, what's sort of interesting here, what's sort of interesting is, again, you want the area inside the rows and outside the circle. Well, so there are three areas here that you're going to need to find. So let me go back into the solution here. Let me stop sharing this and go back into the file. Back to the problem at hand. Okay, so this is a picture of what we have here. Okay, and there's writing. Hold on. Writing here, you don't need to, I mean, you know, it's just old writing. Okay, okay, so the area that I want, again, find the area that lies inside the rows, three-leaf rows, and outside the circle. So this is some area here. This is, well, let me just do one thing here. The circle. You know what I should have done? I should have pressed, oh, they don't have a, they have ellipse. I wonder if that, no, that doesn't work too well. All right, hold on, let me clear that out. All right, let's try this again. Here's the circle. Here's the circle. And you can see the three-leaf rows in black. So the area that you want this area here. You want this area here. And you want this area here. This is the total area. The total area that you need to find. Okay. What can you tell me about the each of these three areas? They are all what? Each area, these three separate areas are all what? They're all equal. That's right, Josiah. So that's an important observation there. So what we can do is, if we can find the area of, say, this first region here, if we can find the area of this first region, okay, and I'm trying to, okay, we can just multiply that area by 3 to get what we want. So what do we have to do now to get the area of that region? What's critical? The region's formed by the intersection of the circle and the rows. So what points do we have to find between the circle and the rows? What points do we need to find? We need to find the points of what? The points of, same thing we did on the last example. We have to find the points of, that's right, Robin, intersection. So I'm going to take the circle and set it equal, the circle r equals 1, and set it equal to the rows r equals 2 to 3 theta, and solve. So a half would equal then sine of 3 theta. Where is the sine of an angle? The sine of what angle equals a half? Well, the sine of 30 degrees is a half, and the sine of 150 degrees is a half. Okay, so therefore, if 3 theta equals pi over 6, theta will equal pi over 18. if 3 theta equals 5 pi over 6, by 3, theta will equal 5 pi over 18. And so the angles where in that the angles in that first quadrant, right? We're talking now, we're in the first one. The angles where the rows in the circle intersect are at theta equals pi over 18, which is 10 degrees, and theta equals 5 pi over 18, which is 50 degrees. And based on the picture here, that looks pretty good. This angle here, and you know, it's not perfectly drawn to scale, but 10 degrees, yeah, okay. And then the other angle, you know, 50 degrees, yeah, that looks about right. You know, so the picture intuitively confirms what you get algebraically. And you'll notice on the graph, I have this little r theta here, this polar coordinate 2 pi over 6. I just drew that. I just like this point here at the tip of the rose is like has the largest radius from the origin, and that looks to be at an angle of 30 degrees and a radius of 2. That's the only reason that 2 and pi over 6 are there. It's just to give context to the graph. Okay, now you found the two angles, and so you know then that the area of one piece is going to be the difference of the areas. So the area will be the integral from pi over 18 to 5 pi over 18 of 1/2 times 2 sine of theta squared d theta, minus the area from pi over 18 to 5 pi over 18 of 1/2 times 1 squared d theta. And so I mean that does make sense. You're taking here. Let me maybe blow that up here. You're taking the area of the petal. Okay, you're taking the area of the petal, and you're subtracting off part of the petal where, you know, you got the circle there. So that's really what you're doing. Are there any questions up to here? Are there any questions at all? Okay. All right, now we have to evaluate these two integrals. And I wrote here it's symmetric about pi over 6, but I'm going to put a little question mark on that. You know, I'd have to check it out. And for this problem, since we got, you know, pi over 18 and 5 pi over 18, I could graph it on the calculator and check, but I just don't want to be bothered with it. I'm going to just, you know, I know these limits are right. Let me just, you know, work through the problem. I mean, I think we can manage it. So I wanted to do this problem where I'm just working through the original limits. So the first integral, okay, so I'd have to check that out if it's symmetric about pi over 6. So right now I don't want you to be distracted with it. I'm going to just cross it out. Not saying it's not true, but I don't want you to worry. So, okay, the first integral, 2 times the sine of 3 theta quantity squared is 4 times the sine squared of 3 theta. 4 times a half is 2. The second integral, you know, is just 1/2 times the integral of 1 d theta. What I'm going to do with sine squared of 3 theta is use the trig identity. Okay, so we know the sine squared of x is equal to 1 minus cosine of 2x over 2. So the sine squared of 3 theta is going to be 1/2 times 1 minus the cosine of 2 times 3 theta, because 3 theta is like x. Are there any questions up to this stage here? Okay, and may I move to the next page? Does everybody have this this copied okay? Oh, okay. So we're working with the original limits. Okay, and now in the first integral, 2 times 1/2 is going to be 1. So I can write the first integral then is just, the integrand is just 1 minus the cosine of 6 theta. And now we have the difference of two integrals. The difference of two integrals is the integral of the difference. So 1 minus cosine 6 theta minus 1/2 is 1/2 minus cosine of 6 theta. Okay, take a moment to write that down. Oh, hi, Alan. Hi, I'm doing my recording for my class. I'm doing it live, but they're copying something down. I saw the email that you sent. Okay, thank you, Alan. Okay. All right. Okay, so now we just get the antiderivative of 1/2 minus cosine 6 theta. That's 1/2 theta minus sine 6 theta over 6. And now we just substitute in the limits. So for this one, I'm not like the last one I said, you know, work needed, you can do the work. Here I'm doing one where I'm actually showing the work all the way. So I put in 5 pi over 18 for theta and where it needs to go. So 1/2 times 5 pi over 18 minus 1/6 times the sine of, okay, if you take 6 times 5 pi over 18, you're going to get 5 over 3, which is 300 degrees. And then you're going to put in pi over 18. So you're going to have minus the quantity 1/2 times pi over 18 minus 1/6 times the sine of 6 times pi over 18. That's the sine of pi over 3. So you really need to show the steps. It's easy to make a mistake on these problems. It's easy to make a mistake, and you know, when you don't show your work and you make a mistake, you can be kind of, I say, lost forever on the problem. But the point is, when you show all your steps, and you know I'm going to want to see that on your final exam for these kind of problems, when you show your steps, when you make an error, if you make an error, it's easier to find the mistake. How many have noticed that with the math? Yeah, John. Thank you. John knows what I'm talking about. Robin knows, and you know, it's and Darius knows. Thank you, Darius. Thank you, Sachi. Absolutely. You know, and the beautiful thing about the exams I've given you and the final exam too is that they're also in a sense of they give you a learning experience, because if you make a mistake and don't get the right answer, you have an opportunity to go back and correct your work, and that's learning. So okay, so the sine of 300 degrees is negative root 3 over 2. So you just draw a 300-degree angle or use a unit circle, and you can look that up. That's negative root 3 over 2, and you just do all the work, and your area is going to equal 4 pi over 36 plus, well, what I'm doing is I'm combining like terms. 5 pi over 36 minus pi over 36 is 4 pi over 36. And then I have 1/6 times root 3 over 2. I have another 1/6, well, negative 1/6 times negative root 3 over 2, but that's going to give me then 2 times 1/6 root 3 over 2. And so your final area is going to be then, well, now hold the phone. This I got to be a little bit careful. This is the area of for one piece, right? We're doing the area of one piece, but the total area, consisted of 3 pieces. So we got to take the pi over 9 plus root 3 over 6, which is the exact area of one piece, and multiply it by 3 to get the final answer of pi over 3 plus root 3 over 2. Okay, and that is the answer. Okay, are there any questions on that? Any questions at all? So the total area is going to be pi over 3 plus root 3 over 2. And it's actually a very lovely answer. I would expect that. Mathematics, when it's done right, is usually lovely. And you could run a computer for 100 years and not have this exact answer, right? So, all right, everybody, I'd like to move to the next example. Are there any questions on this? Are we okay? Okay. So the next example, and everybody had the example copied down, okay, the work and everything. Okay. So the next example deals with it corresponds to the last exercise in your section H.2 exercises. It's an applied problem, okay, and I thought it good you see an applied problem. So it's what I did was I photocopied a page from the book, and it's this exercise here. So let's talk about it. You have what you need to solve the problem, But the problem is you know, well, you get more interesting things sometimes, more interesting numbers when you do applied problems. Although I think we get interesting numbers for our regular problems, right? But let's look at this. So when recording live performances, sound engineers often use a microphone with a cardioid pickup pattern because it suppresses noise from the audience. Okay. So what they have here is they have a stage where the band is, okay, and they have well, suppose the microphone is placed 4 meters from the front of the stage, okay, as in the figure, and let me see here, and the boundary of the optimal pickup region is given by the cardioid 8 plus 8 times the sine of theta, where R is measured in meters and the microphone is at the pole. Okay, so the musicians want to know the area they will have on stage with optimal pickup range of the microphone. So I'm not an expert on, you know, bands and so forth, but I get the impression that if they want to tape a performance live, you know how it is, you've seen videos on YouTube, you know, the audience is shouting and, you know, having fun. Well, they don't want too much outside noise to interfere with the recording of the song. So it's like they're minimizing the audience noise. That's the impression I'm getting from this. This area here, let me just, here is the stage area where the, let me just hold on here. Hold on. Okay, this is the optimal pickup area right here. Now let me be a little bit, and that's the area where you want to find. Okay, so let's look at the solution. I basically took the solution from my instructor's solutions manual to so that, you know, we could just go through how to do this. Okay, so what they have here, and you don't need to copy this down now. Let's just sort of go through it. It'll be in the recording. So we need to find the shaded area in the figure. The horizontal line representing the front of the stage has equation y equals 4. And that's because the origin is right here where the, let me see here, where the, let me be careful here how I phrase it. That's where the mic is, right? At that. Let me be a little bit careful here, one moment. Yeah, the microphone's 4 meters from the front of the stage. Okay, right there. So naturally, we have to find where the this horizontal line here. We have to find where that horizontal line and the cardioid here intersect. So you have to write y equals 4 as a polar equation. So r sine theta would equal 4. Therefore, r equals 4 over the sine of theta. And so where the two curves, where the line intersects the cardioid, is where 8 plus 8 sine theta equals 4 over sine theta. Okay, so far are we good up to this stage? If you have this problem on your final exam, I want to make sure you're comfortable with what's going on. All right. So what they do then is they multiply through by the sine of theta on both sides of this equation. And of course, we're assuming sine of theta will not equal 0, and it will not. If you look at the intersection, you know, this theta equals alpha, that line is one of the intersection points. The other intersection point, of course, would be that line, right? But neither of those angles is 0. So you multiply through by the sine of theta, both sides of the equation. You get 8 sine theta plus 8 sine squared theta equals 4. Then 2 sine squared theta plus 2 sine theta minus 1 equals 0. You can reduce this equation to this here. And you can use the quadratic formula to solve for sine of theta. Okay, because this is like 2x squared plus 2x minus 1 equals 0. It's just you have sine of theta instead of x. So sine of theta, you use the quadratic formula, and you will see that the sine of theta equals -1 plus √3 over 2. That's radian measure for the angle. You have a plus or minus, but you don't use the minus because both of these angles have are positive. You know, theta will equal a positive angle. Like this, they're really focused here on this. Well, let me make it maybe in green. They're focused on this angle here, and that theta is going to be positive. Okay, and the theta is going to be, sine of theta is going to be -1 plus √3 over 2. It's really a beautiful problem. And so then, let me get that off. So therefore, theta would be equal to the arc sine of √3 minus 1 over 2. Okay. So far, and they say the angle is about 21.5 degrees, and it's denoted there by alpha in the figure. Are we okay up to this stage? All right. So what you're going to recognize is that you need to take. I want to be careful here how I phrase it. One moment here. One moment. Okay, so you need to take this area here, okay, you need to take that area and subtract out this yellow area here, this trapezoidal area. If you do that, you're going to get the shaded area. So that's why in the work here, they have the difference of two integrals. But they left out work, right? They left out some work here. So they notice that the 8 plus 8 sine theta quantity squared and the 4 cosecant of theta quantity squared is going to be symmetric. It's going to be, I want to be a little bit careful here. Now hold the phone. I might not be, yeah. The shaded area is going to be symmetric about pi over 2. So they're doing the same thing that I did for the first example we looked at. The normal angle would go from this alpha, which would be the arcsine of root 3 minus 1 over 2, to a top angle, which would be another angle. It would be, I hadn't even thought about this. What I'm talking about is this, this blue angle here. This blue angle here. Okay, so you'd have to figure out what that angle is. Okay, but they say don't worry about figuring that angle out. Just have your integral go from alpha, the alpha angle, which is the arcsine of root 3 minus 1 over 2, and go to pi over 2, and then double that area. So what you'd be getting is, with that integral, is you'd be getting this area here. What I mean is, when you take the difference of these two areas, you're computing then the, well, I'm not saying this right. What you're doing is you're taking, let me do it right here. You're taking this area here, I don't know why I can't. You're taking that area, okay, and doubling it. So 2 times the first integral is double that, double the area in blue. And then take the triangular area and double that. That's going to be the second integral. Okay? And that's how they get, and then they do a little simplification, and they get, they do the work, and they get down to, I want to say this right. They do some antiderivatives, but what I'm trying to say is, like, look at this here. Look at this step here. Okay, is everybody comfortable with the math going up to the boxed, the difference between the two integrals in the box? Is everybody okay up to there? I want to make sure. Are there any questions? Maybe somebody give me a thumbs up if at least, I know you got to look at it more, but are you at least following what's being done? Okay, thank you, John. Thank you, Tyree. Thank you, Robin. Great. So what they do, thank you. So what they do is they do some rather complicated math so they can get to the final answer without using, they get to this final beautiful answer here, and they didn't need to use a calculator, right? And they round the answer off to 204.16 degrees. But what I'm saying is, like, if this problem were on your final exam, if you got up to this integral here, I would not expect you to go through the math they show you here to get to the decimal answer of 204.16 degrees. You could use your calculator to compute this area. Okay, to compute, what I'm trying to say is, once you get to the area in the, hey, let me make a rectangle here. Once you get to this expression in the box. You could use your calculator. You could use your calculator then to approximate that area and get the approximate decimal of 204.16. Okay, similar to, like, remember the hawk problem you had when you had the arc length and you had to find the length that the prey dropped when it was dropped from the hawk, and you had an integral, and you just use your calculator to approximate the integral. Same kind of thing here. Once you get to this integral here in the box, you can use your calculator to figure it out. And of course, the alpha limit is the arcsine of root 3 minus 1 over 2. How many are kind of happy about that? That they don't need for this problem to go through the rest of this beautiful math. I know there's going to be one or two of you, right? Okay, Robin's comfortable. Josiah, great. Now, this is only for this problem, right? The other problems, you need to do the antiderivatives and show your work and show your steps. It's only for this applied problem where you could, once you get to the integral expression, you could then use the calculator. But, you know, as an engineer, you would do that, right? And so the area is 204.16 square meters. That's the area that's going to work in terms of this, hold on, what do they call it? They call it the optimal pickup region in the cardioid. And, you know, this problem, how many have maybe looked at videos on YouTube where the singers are live, you know, maybe like Air Supply or something like one of those groups, and, you know, there'll be an audience, but you'll notice that the audience sound is a bit muffled. How many have noticed that? Maybe in a YouTube video. Has anybody ever noticed that for like a live recording that's done with an audience? That has anybody noticed how well you can hear the band and yet the audience is a little bit muffled? Has anybody kind of noticed that? Or okay, thank you, Robin. Thank you. And yeah, and so, you know, now you at least have insight into that. So this is basically what I wanted to talk about for H.2, and I want to talk about one more example real quick. But is everybody okay with this problem, with this example? Okay, I'll stop the recording now.